You are standing in your hallway at the end of August, looking up at the ceiling, and you can feel the heat coming down through the drywall like an open oven door. The thermostat reads 76, but the compressor on the side of the house is running so hard the meter spins like a roulette wheel, and you already know what the bill is going to look like before it arrives. $341 last July, $390 the July before that. And the part you are not letting yourself say out loud is that the heat you are paying so much money to fight is not actually coming from outside at all. It is coming from directly above your head. Your attic on a hot summer afternoon can reach 60 degrees Celsius, which is 140 degrees Fahrenheit, while the ceiling of the room directly below it sits near 25. And that 35-degree gap between those two surfaces is not a ventilation problem, and it is not an insulation problem. It is energy, continuous and renewable, and sitting between two surfaces of your own house, and nobody is collecting it. There is a small tile about the size of a saltine cracker that you can press against the boundary between those two temperature worlds, and it costs around $4. And it has no moving parts and no battery and no solar panel and no connection to the grid, and it generates electricity quietly all day long for as long as the attic above it is warmer than the ceiling below it, which in most of this country is roughly 9 months out of every year. I want to tell you exactly what that tile is and why it works. And then I want to tell you why it is not already sitting in every attic in every warm climate house on this continent. Because the answer to that last question is more interesting than the device itself. People have been harvesting temperature differences as useful work for thousands of years, and not as folklore, but as actual functioning infrastructure. The badgers of Persia, which are those tall wind towers rising above the desert cities of what is now Iran and Central Asia, were never decoration. They were engines. The builders who raised them understood that hot air rises and cool air sinks, and that the gradient between a sun-baked upper chamber and a shaded lower room could be used to pull a continuous current of cool air through an entire building without a fan, and without electricity because the temperature gap itself was doing all of the mechanical work. Some of those towers are still standing today, and some of them still function the way they did 2,000 years ago. Then, in 1821, a physicist named Thomas Seebeck pressed two different metals together and held one end of the junction hot and the other end cold, and he watched a compass needle deflect from across the room. He did not invent anything that day. What he did was give a name to something the physical world had always been doing on its own. The electrons inside the hotter material were moving, and they were drifting toward the cooler side, and that drift was a measurable voltage. Two materials and one temperature gap, and a current that came out of nowhere except the difference itself. By the late 1800s, kerosene-powered thermoelectric generators were already running scientific instruments in remote Siberian telegraph stations, where one side of the device faced an open flame and the other side faced the cold air outside the hut. And there was no grid and no battery and no moving parts of any kind, just a thermal gap and two materials. And those stations sent signals across an entire empire on the strength of a temperature difference. The principle that runs a $4 attic tile is the exact same principle that runs every steam turbine ever built. And the only real difference is that a turbine needs water and boilers and pressure vessels and a spinning generator the size of a truck, while a thermoelectric junction needs only two materials and a difference in temperature. Researchers at MIT and parallel groups working at Stanford and Berkeley eventually asked a question that seems almost embarrassingly obvious in hindsight, which is whether the thermal boundary between a hot attic and a cooled living space might be exactly the kind of gradient that thermoelectrics need. Buildings were already creating this difference every single day, and nobody anywhere was harvesting it, and the components required to do so were not exotic in any way. Bismuth telluride thermoelectric tiles, which are the same modules used in cheap camping coolers and CPU cooling pads, are commercially available right now for $2 to $6 each. You mount one at the attic floor boundary with the hot face contacting the attic surface and the cool face exposed to the ceiling cavity below, and the building itself becomes the generator. The house was already the device, and somebody just had to notice. Those are real limitations and they matter, but they do not begin to explain why this principle is structurally absent from modern construction. The deeper answer is not technical at all. Thermoelectric modules are manufactured and marketed for cooling applications, and the entire supply chain and the certification pathways and the installer training programs were all built around beverage coolers and CPU cooling pads. Building integrated generation in a passive, low-wattage, no-service form fits none of the categories that building codes or utility programs currently recognize. There is no rebate pathway, and there is no installer certification, and there is no grid tie process for a tile that produces milliwatts. A solar panel has all of those things because a solar panel generates enough revenue to justify the regulatory infrastructure built around it. Utilities have no incentive to promote a generation method that runs outside their metered systems, and the roofing and insulation industries are built around treating attic heat as a problem, requiring their products. And the idea that the same heat is actually harvestable simply does not fit the sales logic those markets have spent 70 years constructing. A tile that lasts decades and needs no service and generates no replacement parts creates no recurring revenue. There is no marketing budget for a $4 tile, and there is no quarterly earnings report for a piece of bismuth telluride. The technology was not buried. It was simply invisible to a system that only rewards what it can standardize and finance and certify and bill for again next month. Now, if you were sitting there thinking this only applies to people designing new houses, I want you to stay with me because this part is specifically for you. You do not need a contractor, and you do not need a permit, and you do not need to climb on the roof. What you need is an attic hatch and a Saturday afternoon. Bismuth telluride modules at the standard 40mm size are available from any number of electronic suppliers for $2 to $8 each. The critical requirement is direct contact with a thermally conductive attic surface, and you do not place the modules on top of fiberglass insulation. Insulation is designed to block heat transfer, which is the precise opposite of what you actually need here. The hot face of the tile needs actual physical conduction. A metal flashing strip nailed to the underside of the roof deck works perfectly. A piece of aluminum sheet pressed against the roof boards and screwed into place works just as well. The hot face goes against that, and the cool face hangs into the ceiling cavity below, ideally in contact with a small aluminum heatsink scavenged from an old computer. You then wire the array through a small MPPT charge controller, which is the same device sold for $10 online to regulate hobby solar panels, and you run the output into a sealed lead-acid battery or a USB power bank. The total component cost for a functional 10-tile array sits somewhere between $30 and $60, and there is no licensed installation required for any of it. The refinement that takes this from a hobby setup into something that pulls steady current for years is in the thermal contact between the tile and the two surfaces it bridges. Most people who try this and get disappointing numbers all made the exact same mistake. They mounted the tile with double-sided tape or with a dab of silicone or with a screw through the corner, and none of those produce a real thermal interface. You need thermal paste, which is the same gray paste sold in tiny syringes for $10 at any computer parts store, applied as a thin, even film between the hot face and the metal plate, and another thin film between the cool face and the heatsink. Then you clamp the entire assembly so that the tile is held under steady mechanical pressure of the kind you get from a small spring clip or a pair of nylon bolts torqued snug. That single change of real thermal contact under real clamping force is the difference between a tile that produces 1/10 of a watt and a tile that produces a full 1.5 watts. Same module and same gradient, but completely different installation. Your attic is not a storage problem, and it is not an insulation problem. It is a demonstration that every building sitting in a warm climate is already balanced across a temperature gradient that physics is continuously trying to equalize. And the only real question is whether that equalization produces waste heat, which you then pay an air conditioner to fight, or useful current, which you collect and use. A device that answers that question costs $4 and has no moving parts. And the fact that it is not already standard in new construction is not a physics problem at all. It is a market problem. Every year, billions of square feet of attic space sit above cooled rooms, generating absolutely nothing, while households pay rising electricity bills and utilities build new generation capacity to meet demand that the buildings themselves could partially offset on their own. The same principle of two surfaces at different temperatures, with a material between them that lets electrons move, was running telegraph stations in frozen Siberia more than a century ago. And it is running the cooling pads inside the laptop you might be watching this on right now. And the only place it is not running is the one place where the gradient is large and free and continuous and entirely wasted, which is the space directly above your head. If you are the kind of person who watches a video like this and feels something settle in your chest, something quiet that says, yes, this is the kind of thing I should already know about, then I want to hear from you in the comments. But I want a specific answer. Tell me what climate zone you live in, or roughly the nearest major city, because the gradient varies enormously between somewhere like Phoenix and somewhere like Portland. Tell me what surface is on the underside of your roof, whether it is bare wood decking, or foil-faced sheathing, or fiberglass batting stapled directly into the rafters. And tell me what you would use the current for first, whether that is a sensor array, or trickle charging a power bank, or running a low-draw LED string through the night. Subscribe if you are tired of treating your house as a bill to be paid instead of a system that can actually pay you back. There is a quiet movement of people right now, of men and women in their 50s and 60s and 70s who are recovering one piece of this knowledge at a time. And we are not loud about it, and we are not building any kind of brand. We are simply reassembling something that was scattered across textbooks and patents while nobody happened to be looking. Before I let you go, I want to walk back through a few things because I have already been getting messages from people who built a small version of this setup and told me the output was lower than they expected. And almost every single time, the reason was exactly the same. They skipped the step that does not look like it matters. The first mistake is the surface. People mount the tile against drywall or against a wood rafter, and then they wonder why the current is weak. Wood and drywall are insulators, and they do not deliver heat to the tile face fast enough to maintain the gradient. You need metal in direct contact with a hot surface, and a scrap of aluminum flashing roughly 4 inches by 4 inches, screwed flat to the underside of the roof decking, will give you a heat-collecting plate that feeds the tile properly. The second mistake is the cool side. People assume the ceiling cavity is automatically cool because the room below is air-conditioned, but it is not. The cavity itself can sit at the exact same temperature as the attic if there is no heatsink pulling warmth away from the cool face of the tile. You need a small aluminum heatsink of the kind salvaged from an old desktop computer bolted to the cool face of the tile with thermal paste between them. Without it, both faces of the tile will climb together and the gradient will collapse inside of an hour. The third mistake, and this is the one that breaks the whole project for most people, is impatience. They install the array, and then they check the output 30 minutes later on a cloudy morning when the attic is barely warmer than the room below, and they see a fraction of a watt on the meter, and they conclude that the system does not work. The system absolutely works. The gradient was simply not there yet. Come back at 3 in the afternoon on a clear July day when the attic has been baking for 6 straight hours, and the ceiling below is holding steady at 72, and read the meter again. And the number will be 5 to 10 times higher than what you saw at breakfast. The tile only produces what the gap gives it, and so you have to measure it when the gap is actually real. Do those 3 things right: the metal collector plate and the heat sink on the cool side, and the patience to read the output when the day is doing its actual work. Do those 3 things, and you will sit in your living room next August and watch a small green LED on the controller blinking steadily through the hottest hours of the afternoon, indicating that the heat you used to pay an air conditioner to fight is now quietly running a battery instead. $4 per tile and $30 for an array and a Saturday afternoon, and a principle that has been sitting in the physics textbooks since 1821, waiting for somebody to walk it up the attic stairs and finally put it to work.